Hey guys, on this particular podcast, podcast 10.5, it is the most important podcast of this unit.
Yes.
Because you will be using the information in this podcast to help you with your final project.
A very substantial portion of your final project.
One third of it.
Yes.
So it is very important that you pay close attention.
Mm-hmm.
So I think it's a pretty long podcast, sadly, but that's what it is.
It's very important.
But
yes.
It's very important. Okay, let's get into it. All right, here we go. Hey, what we're talking about something called a titration.
Right.
A titration is a type of an experiment. But before we talk about that, let's talk about some important definitions. The first word is a standard solution. What's a standard solution?
A standard solution is something that you know the exact concentration of.
A solution whose concentration is accurately known.
Yep.
Okay, so it's a very accurate known amount of concentration. What does that mean?
Concentration is how much stuff is dissolved in there. We usually measure that in molarity, which is be moles per liter.
So let's say, for example, I have hydrochloric acid. I put this in brackets. I put this in brackets because that means concentration. And then let's say I happen to know its concentration to be 0.0123 molar.
Yep.
So this would be a number, but I know this very accurately to the to 3 significant digits or something like that. That would be a standard solution. I would probably have that in some kind of a container, some flask, and it would be stoppered somewhere and labeled as 0.0123 molar HCl. Caution,
acid,
danger,
whatever.
Yeah.
Now, the reason we need a standard solution when we do titrations is because a titration is an experiment to determine the concentration of a substance.
Or something else about it, not always concentration. But
yeah, oftentimes, concentration or something else. We're going to find how much of the unknown we have, but we have to know something about something else.
Yeah.
A concentration in this case.
So, what is a titration? Well, you kind of led into
look at
that, Mr. Sims. You're like, it is an experiment.
Or experiment.
Or an.
And.
Whatever.
Yeah.
An experiment that uses a burette.
And we'll show you what one of those is here in just a minute. You can sort of see
uses
one in
a
the
burette.
background
That's
there.
a particular device. This is actually a burette in the background. It's kind of hard to see in the big scheme of things. That uses a burette to mix solutions. And solutions was unit 9, right? So that mixes solutions together in very accurate amounts. And then you can really learn lots of things. Should you say inaccurate amounts?
Yeah.
Okay, so that's what a titration is.
And we'll demonstrate start to finish how one
And
of
you're
these
going to
works
do
here
so
in
many
just a minute.
titrations, you're going to be sick of them.
You're going to be a pro.
You're going to be a pro, yeah. Okay, now in every titration, there's what's called the end point.
Yep, and the end point is when you have equal quantities of both the thing that you are titrating and the thing you're titrating with.
Sort of. It's more like equal stoichiometric ratios.
Yeah, well, yeah.
So technically it's when you have stoichiometric ratios. What does that mean? I'll tell you that.
Yeah.
Ratios of the two reactants. I don't think I've ever seen a titration that has more than 2 reactants.
No.
So if I have a reaction A plus B makes C plus D, then I would have equal number of moles of A and B. The moles are the same. Now, if I've got A plus 2B makes C plus D, then technically it's actually, if I have 1 mole of this, I will need 2 moles of this. That is said to be a stoichiometric ratio.
Right.
So it depends on the ratio.
It depends on the balanced equation.
On the balanced equation, yeah. A fancy word. Stoichiometric ratio is the balanced equation.
Yep.
All right, so it's important and we have to figure out how we know that we have reached an endpoint too.
Yep.
And we'll talk about that. Well, speaking of talking about that, I think it's going to best help if we actually show you a experiment. We're going to teach you how to do the titration experiment and actually then talk through some of the mathematics.
Okay. Okay, we're going to demonstrate for you now how to actually conduct a titration experiment. Now this is very, very important because you need to know how to do it for a lab, and you also are going to do this on your final project. So it's very important that you get all the details of what's happening here. So first we're going to introduce you to the equipment that you're going to be using. This is called a burette, this tall, skinny device here. You'll notice that it goes from 0 at the top down to 50 at the bottom. So when you use this, you're always going to start with your solution up here at 0, and you're going to dispense it, and then when you're done dispensing, you turn it off, and whatever the volume is, you just read it. You don't have to subtract it from 50 or anything like that. Just whatever the number is, that's how much you've dispensed. Okay, you'll notice it's on a little stand here. It's called a burette stand, burette clamp. And you'll usually be dispensing this into an Erlenmeyer flask. You've used lots of these. You'll also notice I have a piece of white paper underneath the reaction. This is so you can see the color change take place, because when we use the acid-base indicators, we have a color change, and that tells us when we've reached our endpoint. Now, when we do titrations, typically, not always, but typically what you'll be doing in this class at least, your base is going to go into the burette, okay? Base burette. Now for today's titration, I'm going to use potassium hydroxide. The reason I'm going to use potassium hydroxide is that's the first thing I saw that was a base, that was already made up. I saw some sodium, but it was empty. So we're going to use potassium hydroxide. This potassium hydroxide is 0.20 molar. So this is our standard solution. We know the concentration of this solution. So that our standard base solution is going to go into our burette. Now, when you do your lab, you're going to not know what your concentration is of your base. You are actually going to have to determine the concentration by doing a titration. Okay, so you'll undergo the same process to standardize your base. Okay, so the base is going to go in our burette. Now, there's a few ways to get that in there. The easiest way is to either get a funnel or use a burette with a little flared top and just pour it in there. And we'll do that here in just a minute. But before we do that, let's talk about some other ways that we're going to be dispensing our acid. Okay? Now sometimes the acid that you're going to use is going to come in a solid form. Now this is called potassium hydrogen phthalate. This is what you are going to use when you do these in lab to standardize your base. Okay? It's very simple to start with a solid acid because all you have to do is go over to your balance, and you're just going to weigh it out. And I think at the lab, we usually have you weigh out about 0.5 grams or so. So it's very simple to start with 0.5 grams of your acid. You now know exactly how many moles of your acid you started with. You do your titration, and you can do some math.
And guys, a recommendation when you're doing this is you should add it directly to the flask.
Yes.
Don't put it away and transfer it.
Yeah, if you put the flask directly on and weigh it directly in there, you know you're not going to miss any of it. If you use the little weigh boat, some of it can like stick to it with some static electricity, and you never get it accurately all in there. So yeah, weigh it directly into the flask. Very good. All right, now, other times you may be dispensing a liquid acid. So today we're going to be using an aqueous acid. This is hydrochloric acid that's dissolved in water. I don't know the concentration of this. This is what we're going to determine the concentration of in our demonstration here. Now there's a few ways that you can get the acid, a very accurately measured quantity into the flask. So the first and probably the best way is to use a volumetric pipette. Okay? So on a volumetric pipette, you'll suck it up in here to right on the line here, okay? So, and you'll notice this has a 20. What that means is that 20.00 milliliters will be dispensed if you start from the line and dispense all of it. Extremely accurate way to dispense, but it's kind of a pain because you have to pipette, and some people are not real great pipetters. Probably the best way, might not be the most convenient way. Another way is you can simply get another burette. You can put your acid in another burette, dispense however many milliliters you want. Usually we do 20 to 25 milliliters and dispense it that way. The final way, if you absolutely have to, and this is not the best, not the most accurate way to do this, it'll introduce a considerable amount of error, is you can use a graduated cylinder. So you'll fill 20 to 25 milliliters of the acid that you're going to use.
We don't want you to use that.
We don't want you to do that, and if you do that, you're going to want to use like a 25 milliliter graduated cylinder. You'll have less error in a device that has a volume close to that of what you're going to try to measure out. Don't use 100. Never use a beaker. Never use a flask. Never use whatever, a soda bottle that you have lying around that you're going to try to pour it in there, okay? Those are not accurate ways to dispense liquids, okay? Use the pipette or the burette, and if you absolutely must, very accurately use the graduated cylinder, but we don't recommend that. Okay, so that's the equipment. Let me show you now how to get this set up. With the burette, the very first thing you need to do is you need to rinse the thing. Now you're going to rinse before you start, and you're always going to rinse after you're done. If you leave base in the burettes, it starts to warp the thing on the inside by digging away at the glass, and they're no longer accurate. So never leave an unclean, rinsed burette lying around. Okay, so the easiest way to do this is just to get a little bit of water. Now be careful. Up and down is open, across is closed. Open, closed. Okay, so you're always going to rinse it, and basically you just need to put a few milliliters in there. You're just going to let the water run through a little bit, and you also need to just kind of twist it and twirl it like this so you get the inside coated with the water, and you're going to let it run out. That's going to clean out anything that you have in there. Do that with tap water and then also with distilled water. Okay? And once you've done that, you'll notice that there's still a little bit of water in here. Okay? You don't want that, so make sure that's all out, and we're also going to take steps to make sure that that's all gone as well by rinsing with the stuff we're going to put in there. So I'm going to be titrating with the potassium hydroxide, so I'm going to do just a quick little rinse with potassium hydroxide as well. So in the same fashion, just pour a couple milliliters in there, into the bottom, okay?
Now that's potassium hydroxide, guys, and so he's actually rinsing with the KOH.
Yeah, and what this is going to do is it's going to get rid of any residual water that's in there and replace that with the stuff that we're going to be using to titrate. Because if you have water in there, that's going to affect the concentration of your potassium hydroxide, and it's going to introduce error into your experiment. So I've got a little bit left in there. I'm going to just do the little spinny thing again. This will get any drops that are on the inside of the burette rinsed out with water and replaced with sodium hydroxide. Okay. So now it's rinsed and ready to go. So it doesn't take too long to do that, but you need to do that every time you start a titration. All right, so we're just going to put this on here. I'm going to get my reaction container out of the way. And I'm just going to fill this up to the top. Now hopefully I closed the stopcock down to the bottom. I just realized I forgot to double check that.
It is.
Okay, good. Otherwise you're going to have stuff running all over the place and they're a little bit short. Now it's best to overfill just a tiny bit, and I'll show you why in a minute. So I'm above the zero, but I don't want to start above the zero. So what I'm going to do is just get a little beaker for waste.
It's called the waste beaker.
Yep, so just keep one around that you can, excuse me, dispense waste into. And you're just going to get it right down on the zero to start. Bottom of the meniscus right on the zero. All right, so, oh, did I get it? Pretty close? Okay, so now we're ready to start. So we need to get our acid into our flask. So here's the acid that I want to titrate. I'm going to put 20 milliliters of the acid. Now remember, don't jam the suction bulb down onto the pipette. Make it so you can easily pull it off. Okay. What I've been telling my students lately is when you pipette, just make the suction bulb kind of kiss the top. Don't jam it on there. Just make it kiss the top a little bit. If I can get it up there. Come on, you can do it. There we go. So it takes a few times. This is, like I said, maybe not the most convenient way, but it's definitely the most accurate. Oh, and I missed my line again. Okay. So I'm going to get the meniscus right on my line. Perfect. And I'm just going to dispense this in here. Just letting it drain out. Now notice I'm not blowing on this. I'm not using the suction bulb to blow it out. When you use the volumetric pipette, you just let it drain out by itself. And when it gets all the way done, you simply touch the tip to the liquid in the bottom. There's going to be a little bit left in there, but that's okay. These have been calibrated to have that little bit left in there, because that little bit is the same every time. So just let it run out. Again, touch the tip to the liquid, and you're done. You've just dispensed exactly 20 milliliters. I'm going to write that down so I don't forget. 20.0 milliliters of HCl of an unknown concentration. Okay, now we need to be able to determine when this titration is complete. So the way we're going to do that is we're going to add something called phenolphthalein. Okay, and you'll have little droppers of this lying around the classroom. And phenolphthalein is an acid-base indicator. Now phenolphthalein, I'm going to put about, 2 or 3 drops in there, and it's clear and colorless when it's in an acid, but it's pink when it's in a base. Okay, so I'm just going to swirl to dissolve that a little bit. I'm going to lower my burette so it's nice and ready to go. And what I'm going to do is I'm just going to start to dispense some of the base into the acid until it turns pink. Now, you don't want to overshoot this. You want it so it just, with one drop, it turns and stays pink. Now, there's a few ways we can do this. Now, you can just turn it on and let it run, but that's just a great way to overshoot because you don't really want to do that, okay? Now, a really good way to do this is you just kind of twist. And if you just twist, you'll dispense roughly 0.5 milliliter per twist. and you're not going to overshoot, and it's good to swirl occasionally, and you're not going to introduce too much at a time, because every time it goes by, it just lets a little bit through. All right, now this is going to take a little while, so we're going to pause, we're going to come back, and you'll see when as I approach the end point. Okay, so right now I've just got a few drops dripping into the container, and you'll see that as they drip in, we've got a little pink spot on there, but when I swirl it, it goes away. Now we're getting close because the pink is starting to stay a little bit longer. So I add a few drops, and it's pink, I swirl, it goes away. So the idea is that you want to add enough so that when you swirl, the pink stays for at least 30 seconds. And you really only want that to happen with the addition of 1 drop. Alright, so I'm getting really close here. Just adding a drop or 2 at a time.
So you guys, what you're looking for is it to just turn pink and stay pink with the addition of 1 drop. And the best way to get 1 drop is to do that quick little twist. Mr. Sands is pretty good, so he can adjust the stopcock. That's a valve. Sands, I think you're there.
I think you're right.
Now I'm not sure the video is going to show this, guys, but it is got a pink color tinge to it. There you go. There's just a very slightest pink to that.
That's the kind of pink you're looking for. You want the faintest pink you can actually get.
Yeah.
Okay? Now, I'm going to read my thing here. I have 38.5 milliliters that I added. 38.5 milliliters of KOH. And my KOH is 0.20 molar. Okay, so I know the concentration because it says so on the side of the container. Now, let me just overshoot this real quick. What you don't want is dark pink like that. Okay, if you get dark pink like that, you've added way too much, and you've overshot, and you're going to have to start over. You want the faintest pink you could possibly get. Okay, so what we're going to do is we're going to take these numbers now, we're going to do a little math, and we're going to calculate the concentration of the acid that we didn't know the concentration of.
Okay, now let's do the math. So it's all that the math, isn't it? Hey, so the chemicals that I mixed together, if you recall, here's the table here. I had HCl, and I reacted with KOH, and that's going to make water, HOH, plus KCl. That's the balance equation. It's a 1-to-1-to-1 ratio. Now, if you recall, we had 38.5 milliliters of 0.2 molar potassium hydroxide. So we're going to use the equation MB equals moles. And my molarity was 0.20 molar. My volume was 0.0385 liters. Now remember, this is milliliters, this is liters. So I'm going to get my calculator on here. So I'm going to take 0.2 times 0.0385, and I get 0.0077. So on the table here, I'm going to say 0.00, oh no, it's KOH, 0.0077 moles of KOH. So I'm going to take that as a fraction over 1 and say KOH. I want to convert that to moles of HCl. So I'll say 1 mole of KOH is 1 mole of HCl. That's because the ratio here is 1 to 1. Turns out so you get the same number of moles of each. So that's 0.0077 moles of HCl. Well, moles, molarity is moles divided by liters. So that's my moles and divided by the liters. Now the liters, if you recall, was 20 milliliters of HCl. We used that with the pipette. All right, and so that'll be 0.0200 liters of HCl. So I simply divide these two. So I'll take this number that's already on the calculator, divided by 0.02, and I get 0.385 molar HCl. That's the answer. Okay? Okay, so hopefully now, folks, you have figured out how this all works, and you're going to be doing this in class a lot.
Yes.
So you're going to become a pro.
Many times.
Okay, now this then leads into sort of the mathematics. Once
Right.
you have done the titration, what do you do with all these numbers? Well,
Mm-hmm.
that's what we do. Typically, one thing you oftentimes will do is calculate the molarity.
Mm-hmm.
So here's a typical acid-base stoichiometry problem. This is very similar to what we did in Unit 9. It really is no different,
Yeah.
except it's with acids and bases.
Yeah.
The key thing you want to understand, of course, is the master equation. MV equals moles. So if you can take the molarity times the volume, you can get the moles. So first of all, it is a stoichiometry problem.
Yep, got to have a balanced equation to
So
do
I'm missing
stoichiometry.
HCl and NaOH. I'm going to write this out.
You're going to be
HCl
very familiar
plus-
with this
yeah.
equation by the
this,
time we're done.
This equation you're going to use a bunch, even in the lab, because it uses it for lots of things. All right, so what do I know? All right, I have 50 milliliters of 0.1 molar HCl. So I'm going to write that down. 50 milliliters of 0.10 molar HCl. I'm writing under the HCl, and it takes 14.5 milliliters of sodium hydroxide. So if I do this, the thing I know the most about is the hydrochloric acid.
Always start with the thing you know most about.
So I'm going to do that up here because I don't know space, I think. So I'm going to say M times V equals moles. So my molarity is 0.10. My volume, I'm going to do this kind of quick in my head, guys, is 0.050 molar. Or liters, pardon me.
Liters.
I divide by 1,000 to get to liters. Remember, the liters, or the volume here, has to be into moles. I don't really need a calculator for that one. That's going to be 0.0050 moles, because you multiply by 10th, you move the decimal over one place. So that's actually my starting amount for HCl. I'm trying to find the molarity of the NaOH.
Yes.
Now, the molarity of the NaOH, remember brackets, NaOH, will be equal to moles divided by the liters. But
We
guess
have
what?
liters.
I have the liters. It's 14.5. I have to convert to liters, but I know it. So I just need to find the moles of NaOH.
Okay, well, we have moles of HCl. We
So-
just calculated that up there.
0.0050 moles of HCl. So I have to do a little stoichiometry.
Okay.
And then I'm going to use the mole-to-mole ratio for my balanced equation. It was
Okay.
1 to 1. I don't
Ones,
think I
yep.
balanced it, but 1 mole of HCl to 1 mole of NaOH.
All right, so we have the same number of moles.
It
of
actually
NaOH.
turns out to be the same number. So it's
Yep.
0.0050 moles of HCl divided by now watch how I do this fast, 0.0145 liters, not HCl, of NaOH.
Yes.
Of NaOH.
All right.
And
we
I
just
divide them out, and
and-
I get 0.349, 3 digits,
345.
2, 0.35 molar, I
Yeah.
think, actually.
Yep.
2 sig figs. So that's how you do it. It's
It's
really
actually 0.34. But
0.34. Okay,
Yeah.
close enough. All right, let's do one where we're trying to find molar mass.
Okay.
This is a little more tricky here. Okay, so here we have finding molar mass. Okay, I see a bunch of numbers, Mr. Sams.
I do.
But what I really need
Is an equation.
is an equation. So I've got NaOH reach the equivalence point. We'll talk about how that works when we have a monoprotic acid.
Monoprotic.
acid. So
Yeah.
hold on. So a monoprotic acid has the formula HA.
Ha!
And then we'll react that with NaOH. Now we need to write a balanced equation. Well,
HOH.
yeah, see that neutralization podcast played a role.
Yep.
Plus NaA. Now that's because the sodium has a 1
Right.
charge and monoprotic has it's going to have 1 charge, -1. Okay, so the goal is to find what is the molar mass of this. Well, molar mass, if you recall, is the grams
Grams.
divided by the moles. So if I do the grams divided by the moles, then I get the answer.
Hey, wait. It gives us the grams.
Yeah, let's go back and write down what we know. All right, I have 15 milliliters of 0.45 molar NaOH. So I'm going to write that down. 15 milliliters of 0.45 molar NaOH. And I knew a mass. What was my mass? 0.45 grams. So this was 0.45 grams. Hey, there's that mass, Mr. Sams.
Hey.
So what I'm going to do, I'm going to take the 0.45 grams divided by the number of moles of HA. It has to be of HA,
Yeah.
though. I don't know this number
Not yet.
But once I know it, I'm done.
Yep, let's find it.
So I have a molarity and a volume. Oh,
Yep. M
MV.
times V equals moles.
So if you multiply these together, 0.45 molar times 0.015 liters. Notice I'm playing the liter
Yep.
game. What do I get, Mr. Sims?
0.00675.
0.00675, and that's moles of NaOH.
Right.
I don't want moles of NaOH.
Nope.
I want moles of HA. Then I say 1 mole of NaOH is 1 mole of HA. Now, we've picked reactions realistically. That's not always the case. That are all 1-to-1. That's just kind of just the way these reactions happened. So that's a little bit of a misnomer. But I don't need a calculator. That's 0.00675 moles of HA. Now that number then gets plugged in here, and we take the divide, and we get 67 grams per mole, looks like. So when you divide 0.45 by 0.00675, you get 67 grams in 1 mole.
Yep.
So that would be the molar mass of this particular monoprotic acid.
And I can think of no monoprotic acids with that molar mass.
Yeah, so this is a total
it's a made-up problem. Yeah.
Made-up problem. Okay.
Okay, diprotic acid,
yeah,
same
diprotic
thing.
acid's a little bit different. Because diprotic means it's not HA but H2A.
Right. So really the only difference is going to be in the mole ratio step.
So
Everything else is going to be exactly the same.
H2A plus NaOH makes water plus, now this would be Na2A because A really is going to have a -2 charge.
Can you write water as HOH? It might make it easier to balance.
Yeah, that's true. HOH. And so when I balance that, my sodium's kind of weird here, so I'm going to fix that by putting a 2 here. And I believe that gives me 2 hydroxides. I need a 2 here.
Yep.
So let's see what we know. I don't remember what we had. We had 0.55 grams. This was 0.55 grams. 25 milliliters of 0.45 molar. Wasn't that the same number of moles?
No, we had 15 milliliters
Oh,
last
okay.
time.
Now, again, the molar mass will be the grams. What's 0.55? 0.55 grams of H2A divided by so many moles of H2A.
Which we don't know yet, but we can get.
So stoichiometrically, I'm going to take M times V right here. So 0.45 molar times 0.025 liters. Again, I'm converting to liters quickly in my head.
Yep, 0.01125.
And that's moles of sodium hydroxide. So I'm going to pull that down here and take 0.01125 moles of NaOH over 1. I'm going to say, now watch this, 2 moles of NaOH, because of the 2 in the balanced equation up here, is 1 mole of H2A. So divide by 2 and you get
0.005625.
moles of H2A. Of course, that number then gets plugged in here, and we get a grand number of 98 grams per mole. So that, I got that by taking 0.55 divided by 0.005625, and I got 98 grams in a mole.
Yep.
And that would be the molar mass of the diprotic acid. Hey, how do we know if we've reached the equivalence point, Mr. Sams?
Well, there's a couple different ways.
Yeah.
The way, depending on when you take our class, you might do this in multiple different ways in our lab. So the most common way is to use a color changing indicator.
Yeah.
Okay. So in the very
maybe
common
let's go
one,
back to that.
Yeah, and we we demonstrated that when we showed you the titration. We used an indicator called phenolphthalein.
So, Mr. Sams, how do you know if you've reached the end point of a reaction? How do you know that you've reached that when you get the 45 milliliters of 0.25 molar?
Right. Well, we're going to do that a couple different ways in here.
So, first method would be what?
Using an acid-base indicator and looking for a color change.
So, an indicator, color change.
Yeah. So the most common one we use, and the one we used in the example that we showed you in this lesson here, is phenolphthalein. And we're going to abbreviate it Phen because it's a really long word and we don't like to write it.
Phenolphthalein.
Yeah, exactly.
It's
Now
funny
that one
thing.
goes from colorless in an acid to pink in a base.
So, you're looking for a particular color change.
Right.
So, sometimes it's actually called colorimetric.
Yep.
If you care. Okay, so colorimetrically we can determine by a color change. The second method is by the center of the steepest part of a pH graph.
Yes. So another way you can do it is if you're graphing your data as you add as you add the other reactant as you go through your titration. If you collect all the data in terms of how much you've added and what the actual pH is, you graph that and then you look for the steep spot, which we'll show you here in just a minute.
So let's take a look. So here's a pH meter. So a guy using a pH meter, and then he would have a burette like we showed in the demonstration, and he'd be adding to it, and he'd take. It's really kind of a tedious process.
It is.
You'd have 0 milliliters. You'd have a table, and then you'd record the pH, and so it'd be pH. Now, this would be volume, and this is pH. So 0, maybe the pH is 3.2. At 1.0 milliliter, it's 3.4. At 2.0, it's 3.6, and you would go down till you get to 40 milliliters, and maybe it's whatever. It's a very
lots
tedious
of data collection.
Yeah, a lot of data collection, and you would produce a graph that would look like this. See all the data points that this was done on this particular one, each little dots. And you can see the steepest part of the center. See how it kind of accelerates? Why it accelerates is more of an AP chemistry topic.
Yeah.
And so this is the center of the steepest part. And what you're looking for is this point down here for volume. So this is 34, 35, who knows? You could figure it out mathematically. You don't really care about this axis or this spot right here. What you care about is the volume down right here.
Yep.
It's the center of the steepest part. Okay. Now that's actually for what we call a monoprotic reaction. If you have a di or a triprotic acid, like in some projects that we'll do in this course, this would be a diprotic acid. Actually, no, this is a triprotic acid. In a triprotic acid, that would be H3PO4, you would have the first equivalence point, but you usually don't care about the first equivalence point, but you care about the third equivalence point. And here's the second equivalence point. And the third one is usually not visible.
Yeah, the problem is the third is really hard to reach.
But basically, it's always going to be 3 times. If this is at 10, then the third equivalent points will always be 3 times that if it's a triprotic acid.
And the second would be twice the first if it's a
so
di.
it's at 10 and then
or
20
in the
and then
tri.
30. Yeah, realistically, an experiment would be 12.2 and then times 2 and times 3. This is just sort of a canned one. But make sure you understand that when you're doing these graphs. So there's 2 ways to summarize this. There's 2 ways to know that you have reached the end point by the indicator color change.
Yep.
There's kind of an art for picking which indicator,
Yeah.
but actually it always goes back to this, because this is actually the best way. But if you know what color it changes, you can figure it out, or what pH it changes at. So the center, the steepest part of the plotted pH graph is what you do. But then if you know where that is, you can do this. It depends on what year we're doing this, whether you're going to have to do both or one of these. So hopefully that helps you understand that. I think that's the end of the podcast.
I believe so.
So let's double check. Oh, that's the next podcast. Okay, so we will see you in class. So hopefully this long, very important podcast.
Very important.
You may need to watch it again.
Yeah. And when you're doing your lab, if you know you're going to do the titration lab, you may want to go watch the demonstration that we did one more time so you can see how to do it.
Yep. Okay, we'll see you in class. Bye.